All right, this is just to give you a little help on, actually it's both problems 332 and 335. Basically, they both require you to define an alternate coordinate system. And again, we're talking about Nastran. So let's talk about how we do that in Nastran. So the first problem, 332, asks you to consider modeling a pressure vessel. Let's see, this should be horizontal, with a row of planar elements. So this is supposed to be modeling something like the following. So here we have a pressure vessel with an internal pressure P. So this section here is what's being modeled. All right? Now, it's axisymmetric, so you could use axisymmetric elements, but this would be it really is a planar problem, especially if this is thin through the thickness out of the page, it's plane strain, plane stress, and if it's thick, it's plane strain. Now, the way they ask you to set up the boundary conditions is basically to put it on rollers on these edges, and that is to model the symmetry in theta, okay? And then we can get the pressure in here by putting some forces on here, okay? So these forces would be such that whatever this distance here is, I'll call that S, the force times S is equal to, 2 times the force, wait, I should say this. 2 times the force over that length S should equal the pressure, where we're assuming, again, the pressure is in something like force per length, okay? Because it's for this length. If it's given to you in force per area, then you have to use the thickness to get out the length, right? So it would be, right? If that's in force per area, then it would be the pressure times the thickness, right? So you can get that F is going to be equal to SP times the thickness over, F. Right? That's the nodal force applied to each one of these nodes. Okay? We talked about the distributed loads before, and you can review that if you're not sure about how we get the 1/2. All right. The bigger question is, how do we get this boundary condition? Because this is not saying it's fixed in the one direction or the two direction. Let's say we have global 1 and this is global 2. Now this is fine. This edge is fixed in 2. So this SPC, you cannot move in direction 2, and if you want to, you can say you can't move in direction 3 to hold it in the plane. Now on this edge, it's not fixed in 1 or 2. It's got to be fixed in this direction. All right? So I'm going to call this 1 hat and 2 hat. And you want this actually fixed in 2 hat, well, in 3 or 3 hat, because they're really going to be the same. So you need to define an alternate coordinate system. There's several ways to do that in Nastran. There's there's Coord1 and Coord2, and both of these, there's a Coord1R, CORD1C, and then there's a Coord2R and a Coord2C. Now the 1 and the 2 denote different ways of defining the coordinate system. The R is to define an alternate rectangular coordinate system, and the C is to define an alternate cylindrical coordinate system, okay? And actually, in this case, you can do either or. If you really want to try, you can do a cylindrical coordinate system for all the nodes. And if you did that, then these would both be fixed in the 2 direction, or that's the theta direction, okay? See, that would be the difference. If you do the cylindrical coordinate system, you could impose that at both nodes, and then, you know, the 2 direction for this node would be in the theta, and the 2 direction for that node would be in the theta, all right? But why don't we just do an alternate rectangular system up here and define it for these nodes. So these nodes are going to use the rectangular system to define their local degrees of freedom. So when it gives out forces or you prescribe SPCs, it's likewise going to be in that coordinate system. All right. Well, let's first go back to the Nastran manual. So here is the Nastran manual. And let's look at the grid point part just to see the definition. Now, if you look at the grid point part, you know, we've used grid ID X1, 2, and 3. We've left field 3 and field 7 blank. So these have to do with alternate coordinate systems. All right. Now, the field 3 is really a coordinate system just for defining the positions. So in fact, if you had a cylindrical coordinate system defined here for 3, that would mean that x1, 2, and 3, those numbers would be the coordinates in that cylindrical coordinate system. Well, that's good, and you can use that to define geometries relatively quickly, but the one that's more important for this problem is CD. Okay, this is the coordinate system that gives the frame of reference for the displacements, the degrees of freedom, constraints, solution vectors, etc. Okay, so that's what we want to define. We want to go into field 7 and use the coordinate system that we need to define. All right, so we're going to define a coordinate system. And actually, I think we'll probably use coordinate R2. We'll use coordinate R1. That seems to work. I have more luck getting that one to work than this one. To define a new coordinate system, and then we'll stick that into the nodes on the top edge. For these nodes, we'll use that rectangular coordinate system, and the way we'll do it is, right, setting field 7 for those nodes. Okay, so let's just put some node numbers on here, right? So this is node 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we need to define the hat coordinate system, and we use that for nodes 6 through 11. Okay, and you can't see any of that stuff. Right, we're going to find the hat coordinate system, and we'll use that for nodes 6 through 11. So that's going to be in field 8 of their respective grid definitions. Okay? All right. So let's look at how we define coordinate systems. So let's go back to the coordinate system part here. So the difference between 1 and 2, both for rectangular and cylindrical, is that 2 defines, they both have to use points to define the origin, and then another point that defines, so the first point defines the origin, the next point defines the direction of the z vector, so point 2 is on the z vector, and then point 3 is in the xy plane, I'm sorry, the xz plane. So that defines the location, the orientation of the x coordinate, and then y is perpendicular to it. All right. Okay. The second approach allows you to define it with the actual coordinates of the points. The first one allows you to define it with with actual existing grid points. I kind of prefer this approach because I think, honestly, although I could be mistaken, if I remember correctly, Hypermesh has some issues with this card. It doesn't seem to like it, but anyway, you can fool around with it if you want. I have no issue with that. I just tend not to use it. Okay, so if we look at this particular problem here, that's of interest to us, right? All right. What we want to do is define a coordinate system that lines up here. Now the origin can be anywhere. In fact, I'll pick the origin to be node 1. So we're going to use Coord1R. All right. We'll give it a number. Maybe it's 10. That's the coordinate ID. And then grid point 1. Grid point 1 is the origin. So I'm going to use node 1. That's G1. That defines origin. All right. The second one has to do the z-axis. So this is grid point 2. This defines the z-axis. All right. So I don't have any points in z. So maybe the second one actually might have some benefits to it. But in this case, we're going to have to define another point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's define a point 12. We need to define a grid point 12. It's going to be in global. And then we're going to give it coordinates of, well, it has to be the same x-coordinate. Let's just do it this way. So let's assume this is at 0, 0, although we probably have it somewhere else, right? So then the grid point is going to be x is equal to 0, y is equal to 0, and then z is like 1, okay? This would be grid point 12. So that now sets up the z-axis coming out of the board. All right. So now we need to define something that's in the 1 plane. Well, that's a little tricky. I probably should have picked a different node. So here would be the one direction, right? I don't really have any points on here, so actually, now that I think about it, I probably should have put the origin here at node 11. So let's change the origin to node 11, and we'll change grid point 12, the one that defines the z-axis, to have the same, whatever it is, the x-coordinate for grid point 12, okay? And now if that's the case, all right, then you can define any one of these nodes that lie in the x, z plane to be the third grid point. So for example, you could use grid point 9. So this defines the x hat direction, okay? You can see that picture again a little more clearly just before here, right? So this is the origin, the second point defines the z location, and then the third point gives you the x location, or the xz plane, okay? So this now is going to define this coordinate system, and it's located right here, all right? So again, for nodes 6 through 11 in field 8 of their grid definition, you're going to use this ID 10, okay? And that's going to specify that you use that coordinate system for those nodes. Now, when you do that, what does that physically mean? Well, now that we've defined these to use this coordinate system for all its nodal values, output values, degrees of freedom, so on and so forth. That means if I do an SPC, well, I'll give it some set, 20, at node 9, let's say, and then I fix it in 2 and 3, that's fixing it in 2 and 3 in its local system. And likewise, if I want to do a force, put it load, set 21, at node 11, right? If I give it some value, I think it's the value first. First it's the value, so I'll give it like 100 pounds. That's the value. and then its direction, and you can't see this again, I'm sorry. So it's defining a force at grid point 11 as a value of 100 pounds, and now we give it a direction as 1, 0, 0. That's a unit vector in the x direction, but it's in the x direction for the coordinate system defined at that node. So it's actually going to give me this normal vector, so I don't have to figure out the angle. Okay? That's pretty much it. And then when you run it, when it gives you the displacements in the FO6 file, the nodal displacements are going to be in terms of x1 hat and y2 hat. Okay? All right. Now the second problem has to do with coordinate system as well. It asks you, so this is problem 335. It asks you to basically modify any problem you've done in the past to have an orthotropic material. So in Nastran, this is going to be mat 8. So this is an orthotropic 2D material. Okay? Okay. And if we go and look at the material section, you can see what's going on there. This is just simply a material that has an orientation. So if we go to mat 8, so this would be for modeling things like, composites or wood, or even metals that have been worked in a particular direction, so they have different properties in one direction than the other. So here you can see is the relationship, the stress-strain relationship for the orthotropic material, the 2D orthotropic material. You have to define a Young's modulus in one axis and a Young's modulus in a second axis. All right. So if it were a composite material, and this were the direction that the fibers would go, you might call this the one direction and this the two direction. Okay? And you can't see that again. I have to keep remembering you can't see that. Right? So if we define a composite material, here's the fiber direction, you might call that the one direction and that the two direction. So in fact, if you had this thing meshed up, so here is the part. Well, let's put a hole in it just to make it a little more interesting. So it's a composite material with a hole in it. Right. The elements will, in general, not be aligned with the coordinate system. I mean, they're there just to mesh the part. Okay, however it will go, right? Okay, so each one of those elements, is going to have a mat 8 defined to it, and you're going to have to not only give it the material definition, but we need to tell it that this is the coordinate system and this is the coordinate system, 2, 1, and 2. All right. So, class, I guess there's two. Let's make it a little different. So let's assume that here's the global 1 and 2. This is global. But let's say that your material is such that the fiber direction is actually on a 45. So let's assume that actually if we look at the fiber, it's really defined on a 45-degree angle. Okay? So this means we need to have a coordinate system as follows. 2, or 1, and then 2 would be this way, right? It doesn't matter. You could do 1 down this way, and then 2 this way is fine as well. Okay? Either one. As long as this is now 45 degrees. Okay? Okay? All right. So if you go back and look at this card, this does not have any coordinate system to it. This is just where you define the properties E1, E2, and then there's a G out of the plane. You don't have to worry about this too much, but these are the in-plane G's. Okay. This is, I'm sorry, I should just be a little clearer. These are the shear moduli in bending. So these are what are called the transverse shear. So you don't have to worry about this too much because our problems are all two-dimensional. You have to just put the G into here. And you can just pick material properties that you can find on the internet. Okay. So how do we do that for each element? So if we go and look at the element definitions for 2D, here is, well, if you look at this field 8, no wait, field, where is it? Oh, this is the property card. I'm sorry, it's in the actual element card itself, right? Field 8 here, here's the element card, and you have the same field for the triangular elements. You have a theta or a material ID system. So you can either define an angle or an alternate materials coordinate system. Now the problem with the angle is that the angle theta, oops, it's up here. The angle theta is the material property orientation angle in degrees, but it is defined with respect to an element coordinate system. So if you actually define an element through its grid points 1, 2, 3, and 4, that sets up an element coordinate system. So basically, there's an element, the x-axis for the element is the one that splits the sides 1 to 4 and the side that connects 2 to 3. All right. Z is perpendicular to that out of the plane, and then the y is, in the element plane but perpendicular to the x-axis. So that material angle is defined, well actually the material angle theta is defined relative to the edge G1, G2. Now that's fine if all your elements are aligned in the same order and you have your connectivity the same way. But if your elements become general, or even in this case, if the numbering doesn't stay such that this is always G1, you have to figure out that angle theta for each element. And that's definitely a bit tedious. So I think the better approach, obviously, is to, instead of worry about the theta, define it with the alternate coordinate system. So again, that goes back to defining this coordinate system using Coord, Coord 1R or Coord 2R, just like we did before. So you'd have to have some points or define some points such that this would be grid 1, grid 2 would be coming out of the board. Then the third grid point would be along the x-axis, along that 45. And then you give that coordinate system an ID, and that's what you're going to use in each one of the elements in that field 8. Okay? And if it's an integer, not a floating point number, it knows that that's a coordinate system and not an angle. Okay? So that's how you do those problems. I think that's pretty much all you need to know for doing those.